Welcome everyone, and welcome to Bird Math. This is part 2 of the two-part series regarding Riemann sums and definite integrals. If you haven't watched part 1 yet, I strongly recommend that you do so because you might be lost. And in this part 2, we're going to be focusing on finding exact areas of areas under curves. So in part 1, we were given this function f of x equals 1/4 x squared on the interval from x equals 0 to x equals 6. And we were given the task to find the area under the curve, this blue shaded region. Well, we didn't know how to find it exactly, but what we did do was find a way to estimate it. And in this part, I'm going to show you a way to find the exact area of this blue shaded region and how that relates to the topic of integration in calculus. What we did in part 1 to estimate this area was we took the interval from 0 to 6 and we partitioned it into 6 equal subintervals. We created 6 rectangles of equal width. And we noticed that when we summed the areas of each of those rectangles up, meaning area of rectangle 1 plus area of rectangle 2, etc., all the way up to rectangle 6, we got an estimate for the area under the curve. Now, because we used right-hand endpoints in creating our rectangles, this was an overestimate. And this area shaded in green here is the part above the function. It was an overestimate. Now, just to recap, the number of subintervals that we created is n. So in this case, it was n equals 6. Delta x is the width of each subinterval or rectangle. A is the starting point of the original interval. So in this case, 0, and b is the ending point. So in this case, 6. It's the lower bound and upper bound of the area under the curve from 0 to 6. Now, when we used all this information, we plugged it into this formula, which is a sigma notation, which essentially says, find the area of each rectangle and then sum them up together. Our x sub I formula for right-hand endpoints was a plus delta xi. And when we did that with n equals 6 and using right-hand endpoints, we got an area estimate of 91/4. It's around 22. So, okay, great. That's not accurate, and it's an overestimate, but it's a starting point. And here's the part where we need to think a little bit about what would happen if we decided to use a bigger n. In other words, more rectangles. Notice here that this is just a picture using graphing software of our function f of x equals 1/4 x squared partitioned into 6 subintervals of equal width. And this is the area that you get when you sum the area of each one of those rectangles. So in this case, when n equals 6, we got 91/4 or 22.75. But what happens when we increase n to 12? Well, notice each rectangle is still hanging out over the function, so this is still going to be an overestimate. And in this case, we got an area of 22.31 when we use 12 rectangles. Okay, let's increase our rectangles again. Here we use 20 rectangles. And for this area estimate, we got 19.37. Still an overestimate, as you can clearly see. What about when n equals 30? Well, still an overestimate, but in this area estimate, we got 18.91. What about when n equals 60? Well, in this case, we got our area of 18.45. And you should notice a pattern here that as n is increasing, the area of each rectangle that hangs over the function, the overestimate, is getting smaller and smaller. So when n equals 100, yeah, it's still an overestimate, but each one of the rectangles, the area hanging over the function, is smaller and smaller. So for n equals 100, we got an area of 18.27. And when n equals 200, we got an area of 18.14. Notice the pattern that as n increases, area was not jumping all over the place. The area kind of seemed to be converging on a particular value. When n equals 6, 22, n equals 12, 22, n equals 20, 19.37, 30, 18.91, 18.45, 18.27, 18.14. So this should remind you of the fundamental calculus topic of limits. And I'm going to state the following. The exact area under the curve of f of x, which is 1/4 x squared, from 0 to 6, well, here is our formula that we used in part 1. The summation from I equals 1 to n of f of x sub I times delta x. I'm going to say that the area under the curve is exactly this when we take the limit as n goes to infinity. So as n increases, our estimate gets more and more accurate. And we have a technique in calculus for finding out exact values as n goes to infinity. They're called limits at infinity. And it turns out that this is correct. And it also turns out that this is equal to the definite integral from a to b f of x dx. So what we're going to do using this formula, this Riemann sum formula, we're not going to assign a specific value to n like we did in part 1 when we picked n equals 6. We're just going to leave it as a variable and see what happens as we let n increase without bound. Our x sub I, which if you remember, for right-hand endpoints is a plus delta xi, is still the same. And another thing is that our delta x, before we got b minus a over n, which is the formula, we picked a specific n of 6, so we got a specific delta x value. Here, we're going to leave n as a variable. So if you remember, our b was 6 minus 0 over n. We're going to leave n as a variable. And our delta x is going to be 6 over n. Well, now that we have our delta x, we can find our x sub I, because our a is still 0, plus delta x is now 6 over n I, which is equal to 6i over n. And so now this is our x sub I, 6i over n. So the area under the region of f of x from 0 to 6 is equal to the limit as n approaches infinity of the summation from I equals 1 to n f of 6i over n times Well, delta x is just 6 over n. And again, just to reiterate, we're not picking a specific n here. We're going to let n stay a variable and see what happens as we let n tend to infinity. Because clearly, as we showed before, as n increases, as the number of rectangles increases, the more accurate the estimate of area becomes. So, f of 6i over n, the original function is just 1/4 x squared, so we're just going to plug that in. Now, this is just, from here, this is just algebra, at least until the end when we take the limit. So, first of all, constants can come out in front of the sigma. So we square 6i over n, square the numerator and the denominator. Now, n is completely independent of the dummy variable I in the summation. So we can also pull out the n's and any other constants. Okay, and at this point, you should see that, well, we're at the point where we have a summation from I equals 1 to n of I squared, which, if you remember from the last video, we have that nice formula that tells us what to do in this case. And here it is. It's n times n plus 1 times 2n plus 1 all over 6. You'll see why I didn't multiply out this 36 times 6, because now they cancel with the 6 on top. And we can multiply out these n's, so we'll get n squared plus n that's just over 1 now. (36) divided by 4 is just 9. So this whole thing just becomes 9 over n cubed. And this top here becomes 2n cubed. We're going to FOIL this out. Plus n squared plus 2n squared, so plus 3n squared plus n all over 1 combine our fractions there. We can definitely pull out an n here. which will cancel with 1 in the denominator. Which leaves us with 18n squared plus 27n plus 9 over n squared. Now, from here, that was pretty tedious, I won't lie, but from here, just very simple limits at infinity techniques. We notice here that the degree of the numerator and the degree of the denominator are the same, but typically the technique for solving limits at infinity of rational functions is to take the largest term in the denominator and multiply each term top and bottom by or divide each term top and bottom by it. So we multiply the top by 1 over n squared and multiply the denominator by 1 over n squared, or divide by n squared. And that gives us the following. This, of course, just becomes 1 n squared over n squared. And so we're left with the limit as n approaches infinity of 18 plus 27 over n plus 9 over n squared. Now we can finally take the limit. If limits at infinity are you're a little rusty in them, check my channel. I'll be posting a video soon on how to solve these and the various techniques. But just know that, and just think about it for a second, as n increases without bound, as n gets larger and larger and larger, what is 27 over n going to be? Because 27 is a constant, and n is increasing without bound. So what's 27 over 100, over 1,000, over 1,000,000, over 1,000,000,000? The whole thing just becomes smaller and smaller, and it goes to 0. And likewise, 9 over n squared also goes to 0. It goes to 0 even a little faster. And so we're left with simply 18 as the exact value of the area under the curve of f of x equals 1/4 x squared from x equals 0 to x equals 6. And that is the power that we have available to us when we use limits. That's the power of limits. And it's a really beautiful thing. And this is probably my all-time favorite mathematics topic. And I really think it's really cool. And I hope you guys do too. Now remember what I posted up there. We're going to check our work to make sure we did this correctly. So I say that a definite integral from a to b, f of x dx, is equal to the limit as n goes to infinity of the summation I equals 1 to n f of x sub I times delta x, where x sub I is equal to a plus delta xi for right-hand endpoints, and delta x is equal to b minus a over n. So, if you're taking a calculus class and someone asks you to solve a definite integral, in other words, solve the area under the curve of a function from a lower bound to an upper bound, you're probably not going to want to do it this way. You're probably going to use the fundamental theorem of calculus, which will be in my next video. But as a preview of that, I can use the fundamental theorem of calculus to check my work. So this right side we just did. and we got 18. The fundamental theorem of calculus using integration is what we're going to use to check it, and that's what this left side is. So we want to solve the definite integral from, if you remember, 0 to 6 of 1/4 x squared dx. And you can pull constants out in front of the integral sign. And we'll use the antiderivative power rule to get the antiderivative of x squared, which is 1/3 x to the third. And the fundamental theorem of calculus says evaluate at b and a and subtract a from b. So evaluate from 0 to 6. Now, 6 cubed is 216 divided by 12 minus 0 cubed is 0 times 1/12 is 0. And this works out to be 18 exactly, which is what we got up here for the Riemann sum. Remember, this main equation here, which is the definition using a Riemann sum of a definite integral, the right-hand side uses the Riemann sum. The left-hand side uses the fundamental theorem of calculus. And again, as a preview, I will show you the fundamental theorem of calculus. If you have a definite integral from a to b of f of x dx, that's equal to the antiderivative evaluated at b minus the antiderivative of a. And the antiderivative is also known as an indefinite integral. So our work checked out. And I hope that you guys enjoy that. I hope that made sense. I hope that you have an appreciation now for where the definite integral comes from and what a Riemann sum is, how it's defined, and the basic concept of as you partition an interval, the number of subintervals, as the number of subintervals increases, and the estimate of your area becomes more and more accurate. And so finally, after 2 parts here, we have found the area of this function 1/4 x squared from 0 to 6. The area under the curve is exactly 18. And that's about going to do it for this episode. I really appreciate you guys watching Bird Math. Please comment below if you like this. Give me a thumbs up. If you guys have any topics you want to see covered regarding calculus or college algebra or pre-calculus or any high school math, and any math at all, really, just shoot a comment on under one of my videos, and I'll try to make a video about it. Appreciate you guys watching, and I'll see you next time. Bye.